Thanks, Girish, for the introduction. So today, so I'm Wala Mustafa, and today I'm going to talk about Coral and Transport UDF, two main building blocks in our LinkedIn's data processing systems and compute engines. If we look at the life cycle of data applications at LinkedIn, we find that LinkedIn runs on a suite of online, offline, and streaming systems that work together to provide the LinkedIn user experience. Users interact with the website maybe to view job posts or engage with the news feed. Site-facing services capture user actions and perform real-time compute, persistence, or generate streaming events. ETL processes continuously copy the real-time data to offline storage infrastructure, but also registers the data as Dali tables. Dali tables are a collection of files and catalog information with well-defined contracts. Contracts include well-defined type system conversions between storage format type systems and compute engine type systems. Contracts also include well-defined schema evolution rules and other semantic information like data completeness watermarks and schemas used for type-safe manipulation of the data. Users can also build virtual views on top of those tables, which we refer to as Dali views, to further present another layer of abstraction on top of those tables. Compute engines such as Spark and Presto access data from Dali tables and views, perform their compute, and may store data back to Dali tables again. Dali tables and views are powered by the Hive metastore, and table metadata is powered by the Iceberg metadata format. File storage layer is powered by the Hadoop HDFS file system, and we are in the process of migrating this to Azure Cloud Storage. Going back to our data applications, insights made in our batch compute clusters are pushed back to our online systems, which again give back insights or recommendations to our users. In this talk, we will be focusing on views, and to unlock their power, we have built frameworks to virtualize their logic and capture their semantics using a unified representation of their logical plans. Such virtualization layer is the one-stop shop for our view manipulation and understanding and rewriting. And it actually consists of two main components: Coral for relational algebra virtualization and Transport UDF for UDF and expression virtualization. So to understand the view ecosystem at LinkedIn, our view authoring processes follow the standard software development process. So basically, views are authored as software projects. They are stored and manipulated in Git repositories. They contain files to define the view SQL and dependency files to declare UDF dependencies that the view might want to depend on. Developers develop their views through the standard software development process. They go through code reviews, testing, publishing artifacts, and deploying. But deploying in this case refers to having the view live in the Hive metastore. In this case, we keep track of the view UDFs by setting table properties that track UDF names, classes, and dependencies that are required to load those UDFs. So on the left-hand side of this slide, you see the input of this process, which is the software development repo that contains the view definition. And the output is ultimately storing the view as a view definition in the Hive metastore, along with a number of properties that define metadata that's required by the view. And mainly those are table properties for keeping track of function dependencies and function names and classes and so on. So how do we layer Coral on top of our views? Given a view definition, Coral first converts that view definition to a relational algebra representation using Apache Calcite. We refer to that intermediate representation as Coral IR. Then, from the standard intermediate relational algebra representation, Coral converts the view definition to a corresponding SQL that can execute on a number of systems. Since currently our input SQL is a dialect of Hive SQL, then views can natively run on Hive. Through our Coral Spark module, we rewrite the view to execute on Spark. In the case of HiveQL, the query syntax is largely the same, but the module also converts UDFs and exposes APIs for UDF registration. Coral Presto rewrites the relational algebra to Presto SQL. And similarly for Coral Pig, Coral rewrites the relational algebra to Pig Latin. Also, through other partner projects in the company, views are also executable on non-batch backends, such as REST services. As we have seen, one side of the conversion is HiveQL to Coral on one side. On the other hand, Coral Presto converts the Coral IR and produces an IR that expresses Presto SQL. Using calcite rel to SQL conversion, the corresponding Presto SQL can be generated. That Presto SQL can include further expressions that didn't originally exist in the HiveQL definition that have been rewritten to match the same semantics, but also executable in Presto. Similarly, for other modules, these modules would also convert the Coral IR into an intermediate representation that is suitable for some target execution engine, maybe Pig in this case, and then produce a dialect that is executable natively on the other engine. In this case, it's Pig Latin. So what kind of capability such infrastructure enable? Logic virtualization with Coral enables flexible language interfaces. For example, users can choose from a wide variety of languages to express their logic, such as GraphQL, Pig Latin, Dataflow style APIs, or Datalog, express their views in those languages, and then still have them executable natively on these engines. The second capability is workload analytics. So for example, given a cluster-wide workload, we can analyze the workload to obtain various insights about most frequently used tables, operations on those tables, or types of operations applied to various columns. And with that, we can enable materialized view selection and optimization. So some popular subtrees can be chosen to be materialized, and queries can be rewritten to execute those subtrees whenever they match another bigger query that can leverage the subtree that has been pre-computed using that materialized view selection process. Also, it enables data governance and honoring user privacy settings. By joining base tables of views with user privacy settings and applying preferred user actions before propagating data to other operators, we can transparently apply settings on behalf of the requesting application. Those user actions may include filtering out rows or obfuscating some column values. View virtualization and understanding also enables propagating metadata from lower base table layers to view level abstraction. Such metadata includes personally identifying columns and also format-specific schema metadata. So now we move on to the other part of the view virtualization ecosystem, which is transport UDFs. So as we have seen in the previous slide, SQL has pretty well understood IR, which is relational algebra, where we can represent operators in standard ways using scans, filters, projects, joins, and group by operators, and so on. However, UDFs don't really follow this pattern. So they are opaque, they use imperative language, and they are not portable or translatable. This kind of inconsistency in UDF APIs and difference between the APIs that the engines provide to write those UDFs result in a phenomena that we call UDF denormalization, which basically is a manifestation of the duplication of the UDFs due to having to express the same logic multiple times in multiple engines, just because developers need to adhere to the APIs of those engines, which also leads to inconsistency, where the duplicate UDFs sometimes diverge from each other's, and it becomes hard to figure out which one is the source of truth or which one corresponds to the actual logic that is intended to be performed from that UDF. With that cycle of writing multiple UDFs, for the same purpose. It decreases the productivity of software developers, and also gets them into this cycle of learning multiple UDF APIs just to cope with new engines. And it can also result in low performance because sometimes people tend to write adapters around those UDFs so that they can be executed in an engine that they weren't originally written for. So they would have to write this adapter that would serialize and deserialize the data coming into and out of the UDF so that it can be read by the engine that is trying to execute those UDFs. And at the same time, the UDF landscape is characterized by two criteria, which we can refer to by API complexity, where like within each engine, there could be complexities that users have to learn and low-level details such as data models or schemas or operations or APIs that together form the identity of the UDF for that engine, and also API disparity, which is the difference between the APIs across engines. So for that, we have been working and actually using in production our unified UDF API that is applicable and executable in a number of engines, which we refer to as transport UDFs. So transport UDFs provide a high-level API to users, very simple, where they can express their logic and focus on the logic, use simple primitives to write the UDF, and at the same time get native executions out of those UDFs that are suitable to multiple engines. So if we take a look at an example UDF that is written in the transport API, we see that it is written, or like it consists of 4 components. First, users extend like the standard UDF API, and that API is parameterized by the inputs to the UDF and the output as well. In this case, the API would expect, or the UDF would expect 2 arrays, and then it would output a map of those 2 arrays. The logic in this UDF is essentially taking 2 arrays, using one as the source for the keys in a map and the other as the source for the values, and merge them together into one map and return to the user. So the other part that user needs to define as part of this API is basically related to the type validation and inference, which is the second and third boxes in this example, where users in this case express that the input is of type array of k. In this case, we're expecting an array. The array can be of any kind. It can be primitive or nested. Further, that doesn't matter at this point. And the second input is basically an array of v, which is another type than k. And then the output is simply map from k to v, which tells the engine or the transport UDF framework how to derive the output type from the input types. That being said, the last part is basically defining how to process the data on a per row basis. So given 2 inputs from a row during query execution, which in this case are 2 arrays, A1 and A2, what do we do with them so that we can output the corresponding map? So basically, as you can see, logic again is pretty simple, where you iterate on the 2 arrays, get one element from the first array, another element from the second array, and then put them into the map and then return the map. So this is what users need to write in order to define a transport UDF. But then how do they get to execute that UDF on another engine or a specific engine? It's very simple. What they need to do is actually to build the project. And in this case, instead of getting one artifact out of their project, they get a number of artifacts. One artifact that would produce a Presto friendly version of the UDF, another artifact that would produce a Hive friendly version of the UDF, and then a third artifact that would produce a Spark version of the UDF. We have also implemented Avro specific version of UDFs, but since at LinkedIn there are no engines yet that use Avro as their data model, that kind of UDFs are not widely adopted or used. But then how does that work? Basically, what we have seen as an example of the transport UDF that we have seen 2 slides ago represents the middle layer of this slide. which is the user-defined transport UDF. Above this layer, we have a wrapper that would make the UDF look like a UDF that a specific engine would expect. So for example, in the Hive case, Hive UDFs extend generic UDFs or a generic UDF class. So that's what Hive would see. And within that class, we would call into the transport UDF that the user has written. But at the same time, Hive doesn't understand the kind of, the type of data model that the transport UDF is written in. And for that, we basically implement those APIs that have been exposed to the user as part of the transport UDF or in layer 2 in this diagram, using Hive-specific data and data types. So basically, whatever we have seen as arrays or maps, data types that the user interact with, those are just interfaces. Their actual implementation is implemented based on what engine they would be targeting. So in the case of Hive or Presto, these would be manipulating native data types that Presto or Hive or Spark would understand. So to the user, the UDF would look like a platform-independent function, but to the engine, it would look like a native UDF to that engine. So both Coral and Transport UDFs are open source projects where they are both under active development. There are many features we're looking forward to add in both. Specifically for Transport, we're looking forward to adding like new UDFs that can be suitable to like a large user base of machine learning scientists or data engineers, such as machine learning UDFs or spatial UDFs. We're looking forward to add new UDF types, such as aggregate UDFs or table functions. And your support is always welcome. So I think we can follow up after the talk if you have use cases or interested in learning more about this framework. So although the words are mine, the work has been done by a great set of colleagues. I put their pictures here. And I guess we're ready to take questions. Thank you so much.
Thanks a lot, Wala. So just a quick reminder again, there is a Q&A button at the bottom of your Zoom. So if you have any questions, please type your question in there and we'll read them out and answer them live. So we have one question from Devesh from Databricks. His question is the view materializing exact or fuzzy? For example, say I have a join with slightly different filters. Would you treat that as same when extracting the materialized view? Thanks. So I think a quick note of clarification, I think he's talking about things like date constants and so forth, right?
Exactly. That's a very good question. So just to clarify, the view materialization slide is basically an infra that can be enabled by this kind of framework. We don't have it in production yet. We've been talking about such feature, but we have discussed this exact question, which is pretty interesting, how to match or abstract away from things or predicates that have been instantiated in different views, but can also be abstracted. So there are two ways of doing this. Again, all these are just like design discussions at this point. Basically remove those predicates so that they don't get in your way of learning the view or finding patterns in the view. Or also you could learn them somehow by, especially in the date case, by correlating them by the actual time the view has ran. So for example, in many of the cases, people would maybe run a view evaluation on the last 2-day partitions or last week partition or last month and so on. If you look at when the view has ran, and if you look also at the timestamps that showed up in those views, you can basically learn a correlation between the timestamps that appear in the view and the actual time, and learn that, okay, so maybe the intention of this view was calling the now function for the end date, and then maybe for the start date, in case if it was for the last week, then the start date would be now -7, let's say, right? So again, like I think the answer to this question is either like completely remove the dates from your view predicates, or try to learn them.
Yeah. So we have another question from Stephen Moy. So a quick request to all the questioners. So if you can also add your company or your organization, that would help us as well, so everyone can know what your interest is as well. So question from Stephen Moy. How does Coral handle the binding operation? So resolving a symbol to a particular table. Since many engine-specific uh, details has many session-based schema search paths, does the Coral IR handle the binding as well?
Yeah, I actually had a longer version of this presentation, which might answer this question. Let me bring it up from my other presentation. It has a slide that might explain this. Okay, so I think this might be the answer to your question. So basically, like our tables reside in the Hive metastore. And then to make Coral aware of those tables, we need to connect to the Hive metastore and then bind the tables there. And basically that happens through some calcite APIs that we implement to make like our LinkedIn or Dali specific views understandable by calcite, and at the same time allow calcite to connect to the metastore to extract the metadata of those tables and schemas and make calcite also understand the Hive type system. So basically, calcite exposes a number of APIs, which is calcite schema or calcite table, which can be implemented in a way that allows you to supply a metastore client or using a metastore client that you get from the engine. In this case, it could be Presto or Spark, where there is a metastore client already in hand. And then using that metastore client, we implement the calcite schema and calcite table using like methods to connect to the metastore and learn about the tables, their schemas, and then help calcite do its semantic analysis on top of them. And at the same time, we have another layer that binds our functions that are part of the view definition into the calcite SQL operator table through the Dali operator table, which is another implementation that also makes calcite aware of the UDF and the UDF inference and validation that is required again for the view analysis and understanding.